What if I told you that immortality might actually be worse than death? At least if you're trying to solve an algorithm problem. Today, we're killing off Fibonacci's rabbits, literally, and the solution is going to blow your mind. Stick around because this tiny modification to a classic problem reveals one of the most elegant patterns in dynamic programming. Welcome back to Bioalgorithms. Today we're tackling another fascinating problem from Rosalind, Mortal Fibonacci Rabbits. This is part of our ongoing series on coding interview questions and bioinformatics algorithms. So if you're new here, make sure to hit that subscribe button and ring the bell so you don't miss any future videos. Now, before we dive into today's problem, let's do a quick recap. In my previous video on rabbits and recurrence relations, I'll link it in the cards above and in the description, we explored the classic rabbit recurrence problem. In that problem, we had immortal rabbits. Yes, immortal. They never died. Each pair of rabbits takes 1 month to reach maturity, produces one new pair of offspring every month after that, and lives forever. This gave us the beautiful Fibonacci recurrence relation, f of n equals f of n minus 1 plus f of n minus 2, where f of n minus 1 represents all the rabbit pairs from the previous month, and f of n minus 2 represents the new offspring from mature rabbits. Simple, elegant, and it produces that iconic Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and so on. But here's the thing. In nature, nothing lives forever. So what happens when we introduce mortality? Today's problem adds a realistic twist. What if rabbits die after a fixed number of months? Here's the setup. We're given two positive integers, n up to 100, which is the number of months we're simulating, and m up to 20, which is the lifespan of each rabbit pair in months. Our goal? Calculate the total number of rabbit pairs remaining after the nth month, given that every rabbit pair dies after exactly m months. Let me paint you a picture. Imagine m equals 3, so rabbits live for 3 months. This means each pair can only reproduce twice before dying. Month 1, we start with 1 pair of babies. Month 2, that pair matures, so we still have 1 pair. Month 3, first reproduction occurs, so we have 1 adult pair plus 1 baby pair, which equals 2 pairs. Month 4, here's where it gets interesting. The original pair dies because they've lived 3 months, but we have new offspring, so we have 2 pairs total. So how do we solve this? The beautiful part is that we only need to make one modification to our Fibonacci recurrence relation. Think about it. Each month we have 3 things happening. First, all rabbit pairs from last month survive if they're not too old. That's f of n minus 1. Second, mature rabbits produce offspring. That's f of n minus 2. Third, old rabbits die. And this is the new part. Which rabbits are dying? The ones that are exactly m plus 1 months old, because they've lived for m months. So the modified recurrence becomes f of n equals f of n minus 1 plus f of n minus 2 minus f of n minus m minus 1. Let that sink in, or subtracting the rabbits that were born m plus 1 months ago because they've exceeded their lifespan. Alright, let's translate this into Python code. I'll walk you through it line by line. First, we set up our parameters. We want to know how many rabbits we have after 36 months, where each rabbit lives for 5 months. We create an array to store our rabbit populations for each month. We make it n plus 1 in size, so we can use natural indexing, x of 1 for month 1, x of 2 for month 2, and so on. Here's our base case initialization. Technically, month 0 is a bit of a mathematical convenience, but months 1 and 2 both start with 1 pair. Why? Because in month 1 we have our initial pair, and in month 2 they haven't reproduced yet, they're still maturing. Now comes the interesting part. We start from month 3 and go up to month n. This is where we apply our recurrence relation. Notice this conditional. If we're still within the first m months, we use the classic Fibonacci formula. Why? Because no rabbits have died yet. They haven't lived long enough to exceed their lifespan. But once we pass month m, we use our modified formula. Now we're subtracting x of I minus m minus 1, the rabbits that were born m plus 1 months ago and have now died. Finally, we print the result for month n. This is dynamic programming at its finest. We're building up our solution iteratively using previously computed values, and we only need O of n time and O of n space. Beautiful. Now, I know some of you might be thinking, okay, I understand the code, but I want to see it in action. That's where Python Tutor comes in. It's an incredible tool for visualizing how code executes step by step. Let me run a smaller example so we can actually see what's happening. I'll use n equals 8 and m equals 3 to keep it manageable. Watch as we step through the code. Month 3, when I equals 3, we're at I less than or equal to m, so x of 3 equals x of 2 plus x of 1 equals 1 plus 1 equals 2. Month 4, when I equals 4, still, wait, 4 is greater than 3, so now we use the modified formula. X of 4 equals x of 3 plus x of 2 minus x of 0. X of 4 equals 2 plus 1 minus 1 equals 2. See that subtraction? We're removing the rabbits from x of 0. They've lived 4 months, exceeding our lifespan of 3. Month 5. x5 equals x4 plus x3 minus x1 equals 2 plus 2 minus 1 equals 3. Month 6. x6 equals x5 plus x4 minus x2 equals 3 plus 2 minus 1 equals 4. Month 7. x7 equals x6 plus x5 minus x3 equals 4 plus 3 minus 2 equals 5. Month 8. x8 equals x7 plus x6 minus x4 equals 5 plus 4 minus 2 equals 7. And there you have it, the Mortal Fibonacci Rabbits problem solved with a single elegant modification to the classic recurrence relation. Let's recap the key insights. First, we modified the Fibonacci formula to account for death. F of n equals f of n minus 1 plus f of n minus 2 minus f of n minus m minus 1. Second, we only apply the death penalty once we've passed month m. Third, dynamic programming lets us solve this efficiently in linear time. This problem is a perfect example of how small tweaks to classic algorithms can model real-world biological phenomena. It's why I love bioinformatics. We're not just solving puzzles, we're understanding life itself. If you found this helpful, please give this video a thumbs up. It really helps the algorithm, pun intended. Drop a comment below if you have questions or if there's a specific Rosalind problem you want me to cover next. Don't forget to check out the previous video on rabbits and recurrence relations if you haven't already. Link in the cards. And if you're serious about mastering coding interviews and bioinformatics algorithms, subscribe to Bioalgorithms and hit that notification bell. We've got tons more problems coming your way. The code for this solution is in the description along with links to the Rosalind problem and Python Tutor. Thanks for watching, and I'll see you in the next video. Keep coding, keep exploring, and remember, even in death, there's beautiful mathematics.